Okay, let's dive into this. Welcome to today's Explainer, where we're going to uncover the hidden chemistry of the world right in front of our eyes. Have you ever actually wondered what happens when you stir sugar into your morning coffee, and why, if you dump just a little too much in there, it stubbornly sits at the bottom of the mug? Well, today, we're taking a trip from the macro world of everyday life straight down to the molecular level. We are going to figure out exactly how solutions form and how they reach their absolute limits.
To start off, let's just ground ourselves in reality for a second. Basically, everything around us is a mixture. The air you're breathing in right now, it's a mixture of gases. The food we eat, our own body fluids, the steel holding up the building you're in, the drinks on our tables, the water flowing in rivers, all of these are chemical mixtures. We interact with them constantly, completely unaware of the invisible rules that actually govern them. Now, as you know, not all mixtures are created equal. We generally divide them into two camps. On one side, we've got homogeneous mixtures. These are perfectly uniform throughout. Think of a flawless saltwater solution. Every single drop tastes exactly the same because the salt is perfectly, evenly distributed. On the flip side, we have heterogeneous mixtures. These are non-uniform. Imagine taking a handful of sand and dumping it into a glass of water. No matter how hard you stir that, the sand is going to settle, and the top of the water is going to look very different from the bottom. But today, we are focusing entirely on that first category, the perfect, uniform, homogeneous solutions.
Section 1. Building an unsaturated solution. The experiment begins. Okay, before we mix anything, let's just quickly nail down our core vocabulary. These three terms are literally the bedrock of what we're doing today. First up, the solute. This is the substance that gets dissolved. In our case, that's everyday table sugar. Next, the solvent. This is the heavy lifter doing the dissolving. For us, water. And finally, the solution. This is simply the outcome of the two. Solute plus solvent equals solution. Sugar plus water equals a sugar-water solution. Just keep that basic equation in the back of your head. Let's start the experiment. Picture a transparent glass beaker. We pour in exactly 100 grams of water, and we check our digital thermometer just to make sure the temperature is perfectly stable. Now we add a modest 5 grams of table sugar. We take a glass rod, give it a good stir, and watch closely. The solid sugar crystals completely disappear. If we could zoom all the way in, we'd see those sugar particles breaking off the crystal surface, instantly getting swarmed by water molecules and spreading evenly throughout the beaker. There is absolutely no visible sugar left at the bottom.
What we've just created right there is an unsaturated solution. The key word to remember here is capacity. The water in that beaker is essentially shouting, "Hey, I have plenty of room left." Because there is still plenty of available water to surround new sugar molecules, more sugar can absolutely still dissolve. It's unsaturated.
Section 2. Hitting the saturation point. Pushing the limits.
So, we go back to our beaker. Let's push it. We add another 5 grams. We stir, and yup, it dissolves. But the water is starting to get a bit crowded. So we push even harder. 10 grams, 15 grams, 20, 25. With every single batch we add, the dissolving process becomes noticeably harder. The concentration of dissolved sugar is shooting up. And then, bam, we hit a wall. We drop in just one more portion of sugar, we stir like crazy, but nothing happens. The excess sugar just sinks and settles as a solid little pile at the very bottom of the beaker. We have completely exhausted the water's capacity.
We have officially reached a saturated solution. By definition, this means the solution contains the absolute maximum amount of solute that can dissolve in a specified amount of solvent at a particular temperature. Actually, I want you to really lock on to that last phrase, at a particular temperature. Seriously, remember that. We'll see why it matters so much in a minute, but visually speaking, you know a solution is completely saturated when you see that extra solute just sitting there, stubbornly undissolved at the bottom. And this brilliantly illustrates the difference. Notice the clear visual contrast between these two states. On the left, our unsaturated phase. It's clear, uniform, ready for more. On the right, our saturated phase. It has taken absolutely everything it can handle, and the visual proof is that leftover pile of solid sugar right at the bottom.
Section 3. The molecular perspective, the invisible dance. Think of this whole thing like a molecular traffic jam. In the unsaturated state on the left, water molecules are just zipping around, freely grabbing onto the sugar molecules and carrying them off. There are more than enough hands available in the water to grab all the sugar. But look at the saturated state on the right. The water is totally at capacity. Now here is an amazing secret. The process hasn't actually stopped. It's a dynamic interaction.
Sugar molecules are still breaking off the solid crystal at the bottom, but at the exact same fraction of a second, already dissolved sugar molecules are falling out of the liquid and reattaching to the crystal. They're literally swapping places. Because this happens at the exact same rate, there is no net dissolution. It's this perfectly balanced, invisible dance. Section 4. Temperature and solute variables. Changing the rules. Okay, this is where our digital thermometer becomes the most important tool in the room. Solubility is heavily dependent on temperature. That is why every time a chemist defines a saturation point, they absolutely must state the temperature. If you turn up the heat, the water molecules start moving faster and spreading further apart, which fundamentally changes their capacity to dissolve solids. Change the temperature, and you instantly change the rules of the entire game.
Now, what's really interesting about this slide is how entirely different substances behave under the exact same conditions. We've got two beakers here, both with 100 grams of water, both held perfectly at 20 degrees Celsius. In beaker 1, we try to dissolve standard table salt, sodium chloride. We hit the saturation wall at just 36 grams. But look at beaker 2. Table sugar. We can pump a staggering 203.9 grams of sugar into that exact same amount of water before it maxes out. Guys, the water is holding twice its own weight in sugar.
Now you might be thinking, well, maybe sugar molecules are just way smaller. No, actually scratch that. It's a huge misconception. Sugar molecules are quite large. The real reason comes down to molecular interactions and structure. Salt is this rigid ionic crystal lattice. Water has to really work to pull apart the positive and negative ions. Sugar, on the other hand, is absolutely packed with polar groups that just love water. The water molecules bond with these polar groups so strongly and so efficiently that an enormous amount of sugar can be pulled into the liquid before the water is overwhelmed. At the end of the day, it's all about the strength of those invisible chemical handshakes. Section 5. Summarizing the science, bringing it all together. So the crucial point is how these four terms interact with each other. Your solute is what you're dissolving, like your sugar. Your solvent is the heavy lifter, doing the dissolving, like your water. If your mixture can still take on more solute without it piling up, you've got yourself an unsaturated solution. But the exact moment you hit maximum capacity and that extra solid hits the floor of your beaker, you've crossed the threshold into a saturated solution.
I want to leave you with a very simple, very sharp memory trick so you keep this straight forever. Whenever you're looking at a mixture, just ask yourself about its potential. If more can dissolve, it's unsaturated. If the maximum has dissolved, it is saturated. Can equals on. Has equals sat. It's really that straightforward.
And that brings us to the end of today's explainer. But before we go, I want to leave you with a question to chew on. Imagine you're standing in front of that perfectly saturated beaker. You've got 100 grams of water, 203.9 grams of sugar dissolved inside, and a neat little pile of extra sugar crystals just sitting at the bottom at 20 degrees Celsius. If you were to slide a hot plate under that beaker and crank the temperature up to 50 degrees, what exactly do you think would happen to those leftover crystals? Think about how temperature changes the rules. Until next time, stay curious and keep exploring the incredible chemistry hidden right in front of you.
Like, subscribe, and join us for more amazing videos!